For the first question in Lab 4, we're basically going to use a workbook exhibit as a prop. Exhibit 1 and beyond the numbers 3.14 is on page 265 in the workbook. Instead of answering the two questions that are there, we're going to answer these two. Write out the null alternative hypotheses in words, and then should the null be rejected, why or why not? As far as the points breakdown for B goes, I think that one's pretty easy to anticipate. It'll be half a point for the yes or no, and then half a point for the why or why not. Part A, writing out the hypotheses in words, is a little bit different, and we're going to go through an example in a minute. That's what's on the next slide. We'll do it with the other exhibit and beyond the number 3.14. But how the points breakdown works, it's a hypothesis test for a difference. So there are going to be two groups. Half a point is the type of number. So if we're comparing proportions or if we're comparing means, getting that part right would be half a point. 1 point for identifying the two populations or groups that are being compared correctly. I suppose that would mean each one of those populations or groups would be worth a half. Half of a point for the specification as far as writing out the parameter is concerned. Half a point for having the right inequality in the alternative hypothesis. And then half a point for having an equality in the null. What's on this slide is what you would do for Exhibit 1 with those two questions that are in our lab, just applied to Exhibit 2. The reason that I assign Exhibit 1 and not Exhibit 2 is that Exhibit 2 has a part that's a little bit murky. It doesn't explain what numerically superior rating is. I'm going to assume that numerically superior means higher. That would affect what the alternative hypothesis would look like. So with that assumption, then we can do this. What you're going to end up with for answers to Exhibit 1, for what you'd actually have to turn in, won't look exactly like this, but they'll look kind of similar, and if you follow what I've got here as a general template, I think it'll work out okay. It's comparing two groups. If you look at what's there on page 266, two groups or two populations. We have stuttering patients who take pagaclone, stuttering patients who take placebo. Then the type of number that's being compared would be a mean because we have quantitative data. It'll be a difference of means, not a difference of proportions. That may not be the way that it works in Exhibit 1. With writing out the hypotheses, the other things that we're going to need would be the specification, which I suppose the specification here is the numerical rating, and then the equality in the null hypothesis and then the inequality in the alternative. What you'd be looking for generally if you're comparing any kind of medicine or any kind of treatment to a placebo is you would want to see if that treatment does better than the placebo. If numerically superior is higher, we're looking for evidence that it's higher for the pagaclone group because that would be evidence that the treatment actually does something. So what I've got there is basically how I want you to write the hypotheses out for the most part. Write out each parameter all the way. Like how I have my null, I have one parameter equal to other parameter. And my alternative is one parameter greater than other parameter. Write them out like that. Like I said, if you want to follow what I have as a template, I think that'll work. These are the adjustments that I wanted you to make in Beyond the Numbers 3.23. Sorry, this is a little bit grainy. I don't know why this didn't come out that well, but I think it's clear enough to where you can see it. The first thing is inside that green box up toward the top. It's comparing an active treatment versus a placebo, so I think that should be a one-sided alternative. That's why I have more effective instead of different. Then in the table, change the 500s to 50s, change the 501s to 51s, and then there's the row of p-values. I don't know how much you're going to need that stuff other than the p-values, and just knowing that everything in the table stays the same except for the sample size. If you go left to right through the columns, so first, second, third, and fourth weeks, that's the only thing that changes. So I think really those are the two pieces that you need. Just that the sample size is increasing, and when that happens, the p-value is decreasing. That's really kind of the important thing to get out of that table to answer those two questions. The material for these two questions is toward the end of section 4.5 in the book and in the notes. What I want for the thing that's listed as number 2, question 4, that's in Beyond the Numbers 3.23 on page 299, essentially just the relationship between those two things. If the sample size increases, what happens to the likelihood of a statistically significant result? So essentially, your answer should be either that as the sample size increases, the likelihood of a statistically significant result increases, or it decreases, or it doesn't have any effect. It's one of those three things. It is right there in the notes for section 4.5, though. So it does say be very specific, but don't worry about it. That's a one-sentence answer. It's just, if this happens to the sample size, this is what happens to the likelihood of having a statistically significant result. That's not a long answer. Number 3, which would be question 5 right underneath it, there aren't too many possibilities here. The answer to this one is explicit in section 4.5 notes, that if you have a statistically significant result, does that mean that you're definitely going to have a practically significant result? Or does that mean that you're definitely not going to have a practically significant result? Or does that not really have any bearing, that it's possible to have one without the other? It's one of those answers, and that's right there in the notes for section 4.5. Beyond the numbers 3.31, question 1. Question 1 is on page 324, but the hypotheses for the test that you need to do and the sample data are on page 323. So the test that you want the alternative to be that p is greater than 0.32. And then your sample proportion is the one for site 17, the one that's in bold. If the sample proportion is 0.45 and the sample size is 100, then when you enter it into StatKey, your numerator should be 45. This is worth 2.5 points. Half a point for picking the correct option on StatKey, so the correct type of randomization hypothesis test. Half a point for having a correct dot plot with at least 5,000 randomization samples. Half a point for having the correct null value specified and therefore correct center in the dot plot. Half a point for the correct cutoff for the p-value, and then half a point for having the correct tail, like whether it's going to the left or right. With the screenshot and StatKey, you want to have the p-value visible in it. You don't just want to have it set up to where it's centered correctly and no p-value there. Number 5, part A. Stating the null and alternative hypotheses and symbols is worth 2 points. Half a point for the correct parameter, half a point for the correct value on the opposite side of the equality or inequality, half a point for the correct inequality in the alternative hypothesis, and half a point for, I guess, the correct equals in the null, or if you want to write the null with a non-strict inequality, that's okay too. For B and C, there are 2 ways that you can be wrong. Ultimately, there are 2 possibilities. Either the new assembly method takes less time on average, or it doesn't. And B and C are the 2 ways of making an incorrect decision. One of those would be concluding that the average assembly time using the new method is less than 42.3 minutes when that's not the case. The other one is not concluding that the average assembly time using the new method is less than 42.3 minutes when that is the case. Those essentially are the 2 answers in some order. I guess you can phrase that a little bit differently if you want. If you want to phrase the null as the average assembly time using the new method is 42.3 minutes, or the average assembly time using the new method is greater than or equal to 42.3 minutes, those would both be fine. The main thing to watch out for is that it's easy to get the errors backwards. Then, part D, half a point for each blank. The last 2 blanks are basically the null hypothesis, because you do everything under the assumption that the null hypothesis is true. And then the first 2 blanks are indicating how you'd get the p-value. Number 6, which is conducting a hypothesis test using a confidence interval. Part A is just matching up the confidence level correctly. That's half a point. In Part B, the confidence interval is in bold because that's not usually the way we do a hypothesis test. Make sure you're finding a confidence interval here, not a p-value. If you're finding a p-value, that's not really the point of this question, and you're probably not going to get a lot of points for that. That's worth 2 points. Half a point for having the correct StatKey option, the correct type of confidence interval that you need. Half a point for having a dot plot with at least 5,000 bootstrap samples, not randomization samples. Half a point for setting up the percentiles correctly, and half a point for the data entry / original sample box. Part C, if that's worth 1 point, you can figure out how it works. It's half a point for the yes or no, half a point for the why or why not. And then Part D, what must be true about the p-value? There are 2 possible answers to Part D. One is that it's less than 0.1, and the other is that it's greater than 0.1. It's one of those two things, and that's all you really have to put there for D. You can answer it based on the conclusion in C, or you can use the confidence interval in B. Either way, but those are the two possible answers. Either the p-value is less than 0.1 or the p-value is greater than 0.1. One of those two things is what you want for D. Number 7 is finding a p-value by counting dots in a randomization distribution. That's why there are only 120 randomization samples, because if I used a few thousand, the dots would be too small to count. This is worth 1.5 points, and the things you have to do here are get the right denominator for the p-value, which won't be too bad, get the right numerator, which you'll get if you have the correct cutoff and the correct tail, and then if you need to double, make sure you do it. So if this is a scenario where you need to double the tail, make sure you do that.